Now let's address the question of how to calculate an equilibrium pH value from initial conditions, namely from an initial amount of acid or base that we'd like to dissolve in some volume of water. So what are some general principles of calculations of this type? Well, we'd like to know the equilibrium pH of an acidic or basic solution ultimately, so what we're going to be doing is solving an equilibrium problem, usually through the ice table approach. And ultimately, the problems described here are just ice table problems taken in context. Our goal is still to find equilibrium concentrations, and in particular H3O+. They may have the added step of using pH is equal to negative base 10 log of the H3O+ concentration at equilibrium, but this is really just a mathematical manipulation to make the answer a little bit more human brain friendly, if you like. And our ultimate goal is finding the equilibrium concentration of H3O+. The general ice approach applies very well to problems of this type. We're going to write a balanced chemical equation and its corresponding equilibrium expression. This is going to involve either Ka or Kb, depending on whether we're talking about an acid or a base in solution, respectively. We're going to calculate Q and then use Q versus K to determine the direction of reaction. Very often Q will be 0, but not always. We're going to prepare an ice table. And then finally, we're going to solve for x and plug in for the value of x to calculate equilibrium concentrations. And then finally, if necessary, we'll calculate the pH from the equilibrium concentration of H3O+. The relevant reactions will always be either acid dissociation or base association, and the corresponding Ks will be either Ka or Kb. Let's talk about strong acids and bases first. Strong acids are completely dissociated. That means that we can go from the concentration of HA initially to an equilibrium concentration of H3O+ that is numerically equal to the concentration of HA that we started with. So for example, if we're interested in the pH of a 0.7 molar solution of hydrochloric acid, we know that this reaction of aqueous HCl reacting with water to form H3O+ and Cl- is essentially 100% complete. And so we can still do an ice table showing that initially we have 0.7 moles per liter of HCl. The change, however, we know immediately to be minus 0.7 moles per liter of HCl here. Since the reaction is essentially complete, we're going to get plus 0.7 moles per liter of H3O+ and plus 0.7 moles per liter of Cl-. The equilibrium concentration of H3O+ then is just 0.7 moles per liter, and that's equal to the equilibrium concentration of Cl-. We can then take this and use the definition of P. pH is negative log 10 of this H3O+ concentration to calculate the equilibrium pH. And in this case, it's equal to 0.15. Ultimately, all we had to do to solve this problem was to take the initial concentration of HCl and apply the P operator to it. The only reason we're able to do this is because of this idea that a strong acid forms H3O+ completely in aqueous solution. Essentially, we're in a situation where we don't need to worry about equilibrium. The one exception to this, which I'll put out there but won't talk about in detail, is that at very small concentrations of strong acids or bases, the natural H3O+ and OH- concentrations in water need to be taken into account on the initial line. Remember, there's 10 to the negative 7 moles per liter of H3O+ in pure water, and the same is true of hydroxide. So if we're talking about strong acid or base concentrations on the order of 10 to the negative 7 moles per liter, we do need to account for these initial H3O+ and OH- concentrations in preparing this ice table. And writing an ice table never hurts, even for this sort of non-equilibrium problem of finding the pH of a large concentration of a strong acid in water. It still helps to write an ice table to organize your thinking. Now let's talk about the pH of weak acid solutions, which is considerably more complicated. The reaction of interest here is acid dissociation, because we're imagining starting with HA, a weak acid, and dumping it into water. The K of interest is Ka for the acid. So let's look at an example. What's the pH of a 0.250 molar solution of acetic acid? Let's just abbreviate acetic acid as HA. It has one acidic proton, that's really all we need to know. And the reaction of interest here is the reaction of acetic acid, HA, with water. The conjugate base, which is acetate anion, we'll just abbreviate that as A-. and H3O plus. This is step one, right? Writing out the balanced chemical equation. The concentration that's given in this problem, the 0.25 moles per liter, that's the initial concentration of acetic acid of the reactant. So we can immediately write that molarity underneath HA on the initial line. The concentration of water is irrelevant since it's a liquid, and initially we have no A minus present and a very, very small amount of H3O plus present, 10 to the negative 7 moles per liter in pure water, right? This is so small relative to 0.250, the initial concentration of the acid, that we can essentially treat this as zero. To clarify what this looks like mentally and how you should be thinking mentally, imagine we had the water and the acetic acid separated by some kind of imaginary partition at this point. So we haven't turned on acid dissociation yet. When we turn on acid dissociation, all of a sudden the acetic acid starts dissolving and reacting, and then the change line becomes relevant. Before writing changes on the change line, we need to consider Q versus K. And in this case, since we started with no A minus and no H3O plus, Q is equal to 0, and so the reaction's certainly going to go forward. We're going to lose some HA, and we're going to gain A minus and H3O plus, and we don't need to worry about stoichiometric coefficients since they're all 1 here, which is quite nice. For the equilibrium line, we simply add the initial and change lines. One convenient thing about problems of this type is that X is often going to be directly equal to the H3O plus concentration, so as soon as you solve for X, you don't need to do any additional, for example, stoichiometry calculations. You can go right to the pH after solving for X. At any rate, it's important now to substitute in to the equilibrium expression these concentrations. So writing the equilibrium expression is an important first step as well. We're going to have the concentration of the products, H3O plus and A minus, divided by the concentration of the reactants at equilibrium. And taking the concentrations off of the equilibrium line, we get x squared in the numerator and 0.250 minus x in the denominator. And from here, since we know that this is equal to 1.8 times 10 to the negative 5, this is the given Ka value, we can solve for x directly. To solve for x, we could multiply both sides by 0.25 minus x and use the quadratic formula, but a convenient simplification, and one that is often valid when Ka is very small, here it's about 4 orders of magnitude less than the initial concentration of acid. As long as Ka is sufficiently small, we can assume that x is going to be small relative to the initial concentration of acid. And so we can, in a sense, ignore the minus x in the denominator here. Just multiply both sides by 0.25 and take the square root. So x is going to be equal to 0.25 times the Ka value, 1.8 times 10 to the negative 5. This entire thing to the 1/2 power, which comes out to 0.0021 moles per liter. Conveniently, this just is directly equal to the concentration of hydronium at equilibrium. And so to find the pH, we can just do the negative base 10 log of that value, 0.0021, which is equal to 2.67. This is the equilibrium pH of a 0.25 molar solution of acetic acid. Does it make sense? Well, it should. The pH is less than 7, and that's what we would expect for a solution of an acid, that the pH is less than 7. The hydronium concentration is greater than 10 to the negative 7. It may seem quite small, but a pH of 2.67 helps us see that this is definitely an acidic solution. pH of a weak base solution is done similarly. The reaction of interest now is base association, the reaction of B with water, and the K of interest is Kb for the base. So let's work through a quick example using ethylamine and again a 0.250 molar solution. So the reaction of interest here is ethylamine, which I'll just abbreviate as B, it's a neutral base, reacting with water to form its conjugate base, which contains an additional proton, and hydroxide, OH-. Initially, we have 0.250 moles of the base in solution. Water is irrelevant, and we have no Hb+, and essentially no OH- using the approximation that the initial concentration of base is far, far greater than the 10 to the negative 7 we would expect for the concentration of hydroxide in pure water. So with that out of the way, we can now assess Q versus K and notice that just as before, the initial Q is equal to 0 since we haven't, in a sense, turned on base association just yet. There's no HB plus present in the initial mixture. So on the change line, the reaction is going to go forward. We're going to get moles per liter of products, HB plus and OH minus, and we're going to lose moles of reactants. And we can write the equilibrium line just as we did in the previous example, 0.250 minus X, positive X for HB plus and positive X for OH minus. We then set the equilibrium expression equal to Kb and write it out explicitly. Here it's the conjugate acid concentration times the hydroxide concentration divided by the concentration of the original base. And we can plug in the values that we got from the equilibrium line, and that is collectively equal to 5.6 times 10 to the negative 4. This is the given Kb value. In solving for X, here again we can assume that because the initial concentration of base is so large compared to the Kb value, the change in the initial concentration of base will be minuscule in comparison to that initial concentration. So we can essentially ignore the minus X in the denominator and solve for X as we did before. When we solve for X in this way, we arrive at a value of X equal to 0.0118 moles per liter. And now it's very important to recognize that since we're dealing with a base association equilibrium, this is equal to the concentration of hydroxide at equilibrium, not the concentration of H3O+. But the problem stipulates that we're interested in the pH. So how do we go from this to a pH value? There are a couple of different ways to do this, but my favorite way to do it is to calculate the pOH and then take 14 minus that to find the pH. So to do the pOH, we simply do the negative base 10 logarithm of that concentration of hydroxide at equilibrium, which is 0.0118. That comes out to be 1.93, and we can then calculate the pH just using 14 minus the pOH, which in this case is equal to 12.07. This is the equilibrium pH of this basic solution. And this should make sense. It should make sense that writing down a pH of 1.93 for a basic solution doesn't make sense. That would be an acidic pH, but we've added a base into solution that's going to remove H3O+ from the solution. The pH is much higher than 7 when a base is added. And here we've got a pretty hefty concentration of a base with a decently high Kb value, around 10 to the negative 4, which gives us a fairly high pH value, 12.07.